All right, and everybody managed to run. Um, the expected way in which we were trying to run was like this: Python and run, use the file name, and we would get the output. And I'm going to try to put this a little bit higher so that everybody can see, right? And we went so fast through it that we have not explained the code very well, right? Remember, we're following a pattern now, right, of writing functions that compute sequences, okay? And perhaps I jumped the gun a little bit too much, so I'm going to start with this. All right. So one important technique in designing or creating code for this kind of sequences is generalization. We have to generalize. Computing the powers, we were trying to compute the powers of B, and we're trying to compute L such powers, right? A number L. So the length of the sequence was supposed to be L, right? And it's not easy to do that, all right? Because we want to express computations in terms of themselves. So we try to find a more general computation, all right, that is actually easier to compute. And that's an interesting thing, right? Because it seems that when I generalize, I would get something that is more difficult to handle. Actually, in general, it's easier to handle. And I'll give you examples, right? For numbers, infinity was invented, right? And infinity actually simplified things when we talk about numbers, right? It didn't it didn't make things more complex. Why? Because now when you add any two numbers, you get another number, right? You can go as far as you want. Whereas if you have limited range, you would have to think about what if you add two numbers and their result is out of range, right? So you have more cases to handle when you reason about numbers. So what generalization do we do when we want to compute the powers? Well, we're going to say the following. We want to compute a sequence of powers of B. We want k of them, but instead of starting at 1, which is the natural beginning, we want to start at m. So m would be considered to be, would be expected to be a power of B, one of the powers, right? And starting with m, we want to have L powers, L such powers, right? So whenever we have this new statement, we want to compute something that is somewhat more general, right? We have an extra argument or computation. Things are a lot easier. So the first element is going to be, actually, we don't have to have it as m times b, we can have it as m, right? So m would be the first element in our sequence, all right? And we want to compute the remainder, right? Which now instead of starting at m, we can just start at m times b, right? So it's a lot easier to express the larger problem in terms of the smaller one, right? So we say, oh yeah, we still want the powers of b, right? But now, since we have already produced one, we want only k minus 1 of them, and we want to start at m times b now. We don't want to start at m anymore, right? So having added this extra argument and having generalized the problem is actually easier to solve, right? So we use this expression only when k is 0, k is greater than 0, and if k is 0, we return the empty tuple, right? The empty sequence. So this is a helper. It doesn't compute what we want. It computes something more general, all right? And it puts an extra burden on us, the burden of adding an extra argument, right? So let me save this, all right? And before printing the powers, all right? So what have I done here? This character, the sharp, right? The hash turns the remainder of the line into a comment. You can write anything there, and the Python compiler will ignore it, right? So you can use this kind of lines for notes to yourself or to explain to others what your code is doing, or simply to ignore parts of the programs that you don't want being executed temporarily, right? So I'm going to just deal with the helper. I'm going to say print helper of, let's say, on powers of 3. I want 10 of them, and I want to start from 1. All right, because 1 is a power of 3, it's 3 to the power of 0. And I can ignore this part of the program as well, right? So Command S, I'm saving, and I'm going to run this. Right, and as it runs, you can see the powers of 3, and we can see that there's 10 of them in the list. All right, so we've got what we wanted, but we have the extra burden of having a 1 here. I can change this 1 into 27, let's say. 3 to the power of 3. So this has to be a power of 3, right? And if I execute this, we see that instead of starting at 1, now we start at 27. But our original problem statement was, I want all the powers of B, I want L powers of B starting at 1, right? Because of that, right, let me define the powers of B. We want L of them, right? And this will be the helper, B, L, and we're going to fix the first power in the sequence to 1. Yes?
How do you run the code in Python?
Pardon?
How do you run the new code? How do you run the thing in Python so that it will run the new one in the terminal?
I'm going to save, right? So now I don't want this anymore.
Command S.
Right? Command S. Yes. Oh, Command S, that's what you're looking for.
Yeah.
I'm going to run the code again. So now I get all the powers of 2, all the powers, 10 powers of 2, right? So now there's yet another thing that we can do. Because this helper is only useful for powers, we can hide it inside. It's not useful outside of powers, right? Outside of the context of powers, it's simply not useful. So I'm going to go here, and I'm going to insert it inside and indent it properly. Okay? So we get the definition that we used last time, right? So at this point, if I say print helper of, let's say, 5, 10, and starting at 1, we're going to see that the Python will give an error, right? So it has executed this line right here, right? This one has been executed. And when it tries to execute this one, it says, oops, I don't know what helper is. Why? Because helper is hidden inside. Its scope, this is what we call it, the scope, is only inside the definition of powers. This is very useful because when you have large programs, there's a very high chance that you are going to want to use the name helper many times, right? There are going to be many kinds of helpers used in many places, right? So a helper you define there is going to clash with a helper that you define here, right? So if you have this ability to hide the helpers, the functions inside other functions, then you can limit the scope and you can freely use the names without danger of clashing. So Control X will remove the line that was not executing correctly. And let us start a new file for today's lesson. So I'm going to call it week 2 Monday. All right, and let's try to compute more sequences. Another interesting sequence would be the sequence of primes. All right, and again, the sequence of primes is a bit difficult to compute on its own. All right, so I'm going to propose a more general statement. Right, so I want to compute the set of primes from a sequence of numbers in increasing order. All right, starting with a prime and not containing multiples of numbers smaller than the first number in the given sequence. So, for instance, I'm going to write a helper again. And if I call the helper and I want to get it from the sequence tuple, or actually we can use an extra, we can just use brackets. And let's say I start with 5, which is a prime number, and all the numbers slower than 5 are 2, 3, 4. 1 we discount, we don't care about 1, right? So I should not have any multiples of 2, 3, 4, right? So I can have 7, I can have 10, I can have 11, I can have 13, 13, what else? 15, 17, 19, 20 I cannot have. 15 I cannot have, sorry. And 10 I cannot have. 10 is a multiple of 2, right? So 15 is a multiple of 3, I can't have. 20 is a multiple of 4, I can't have. 21 is a multiple of 3, I can't have. 22 is a multiple of 2. 23 I can have. 24 I can't. 25 I can have, right? 26 can't. 27 can't. Pardon? Louder.
But only numbers smaller.
28 I can't have. 29 I can, right? 30 cannot. 31 I should be able to have. 32 can't. 33 can't. 34 is 2 times 17 can't. 35 I should be able to have, right? So if I pass into the helper, I pass this set, the result should be, right, 5, 7, 11, 13, 17, 19, 23, 29, 31, right? So I want from this set, this is the contract, right? This is my assumption, that whenever I have a list like this, my helper can select the primes. Yes? So this is more general than just computing the primes, right? But obviously, if I'm going to start from 2 and put all the numbers from 2 onwards, I'm actually going to get the actual primes. So there is an input that actually solves my problem. Is that clear? Is that clear? There is an input that actually solves my problem. If I put in the list of numbers starting from 2, 3, so if I put in 2, 3 is legal, 4 is legal, 5 is legal, 6, 7, 8, 9, 10, and I would get the primes out of this, right? So the expected output would be 2, 3, 5, 7, and that would be it, right? So there is an input. This would be a tuple, right? There is an input that actually solves my problem, because what do I want? I want to compute the primes. But I'm saying, well, let me compute something more general. Let me take out the primes from a list with these properties. Guess what? This is a list with these properties, right? Yes, but I want a piece of code that works for this kind of lists, right? So the first element is a prime, and it contains numbers in increasing order, but not multiples of numbers smaller than the first. Does it make sense? So I should add another bracket here. So this is what we want to write. This is the kind of helper that we want to write. And this is a very simple function to write, actually. It seems like it's very complicated, but it's actually very simple. The helper, so we're having a tuple here, right? And this tuple has those properties. So my list of primes is going to be what? Well, T0 is going to be there for sure, right? So I'm going to return, and I'm going to have something if len t is greater than 0, else nothing, right? It's pretty much the pattern. And we're trying to figure out what to put in here, what to put here. Okay, so what do we put here? Well, T0 has to be there for sure, right? And we are going to turn this into a tuple, and plus, and what's left? So from the next, but I have to remove all the multiples of T0, right?
Yeah.
Now, yes. I can use again? So I can use a very simple comprehension, right? So I can essentially use any number x, right, for x in t going from 1 to the end if x percent T0 is not equal to 0, right? Right? So this actually would be a list with this property, right? So what can I do with this list? There's one step that we must not forget. Helper here, right? So what are we doing here? We're starting from the next element after T0, right? We're eliminating all the multiples of T0. X percent T0 is all those for which X is 0 are not going to be in this tuple, right? So this is a list, is a sequence that has all these properties, right? Because T had numbers in increasing, T has number increasing order, this will have numbers in increasing order, right? I'm going to remove some of them, but whatever is left is still going to be in increasing order, right? So it has this property. It starts with a prime. How do I know it starts with a prime, right? Well, I have eliminated all the multiples of T0 and numbers smaller than T0, right? So it has to start with a prime. Whatever is in this tuple will start a prime. And it's not containing multiples of numbers smaller than the first number in the given sequence, right? So T already was not containing any multiples of numbers smaller than T0. And now I have also eliminated the numbers that are multiples of T0, right? So I have this property followed as well, right? Yes? So now, let's check that this works. Print helper, and I'm going to make it very simple. Range from 1 to 100. Actually, it can't be 1 to 100, 2 to 100. Okay, and let's see what we have got. So this is week 2. Right, and you see the prime, all the prime numbers. Now, what kind of other inputs can we pass in here? Well, we can actually try exactly this, right? Right, so so again, you see we get all the prime numbers as expected, right? So as long as our contract is in effect, right, this, whatever we put in here has these properties, has these 3 properties, right? It will work. If you put garbage, right, it's going to be garbage in, garbage out, right? But if you put the correct input, it's going to be correct. Nevertheless, right, and let me make it like very clear. Let me put 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? So if I put these numbers in, I'm going to get, right, prime numbers up to 20. So why is that? Because this set, this sequence, simple as it is, has these 3 properties, right? So I'm just going to delete this because it's garbage by this point, right? So convince yourselves, right? So this sequence, all right, so is a sequence of number in increasing order, starts with a prime, which is 2, and is not containing multiples of numbers smaller than the first number in the given sequence, right? 1 doesn't have multiples. 1 is not considered a prime, doesn't have multiples, right? So then everything can be added. So this sequence has the properties then that can be passed in. Now, this is a very trivial sequence, and there are ways of producing it, much easier ways. You have already seen that, right? So I'm going to go here and talk a little bit about generating sequences automatically. So there's this way of generating what we call lazy sequences. They're sequences on demand. One is range, is the simplest. So if I try to generate the range from 0 to 10, right, it will generate all the numbers between 0 inclusive and 10 exclusive, right? So actually it will go up to 9. But it produces this object that contains all the numbers inside, but doesn't contain them explicitly. They will be produced on demand. Whenever we need another number would be produced. Why? Because this saves memory, right? And most of the sequence-generated numbers in Python are like that, right? They don't give you the number until you want to see it. Now this range, if I say x equals range 0 to 10, right? I can say next x. So x becomes a range object. Object is not an iterator. Oh, isn't it? That's interesting, right? So all right. So you can essentially, the numbers are in there. You can use them whenever you need. Then we have the non-lazy, the eager collections, the eager sequences, which are tuple, list, set dictionaries. And whenever we want to convert, there's a very easy way of doing that. I can just, if I want a tuple, I'm going to put tuple around. This will waste memory, but our memory demands are not that high. And then you can actually see the sequence. If I put this sequence into, as I did already, range of 0, 10, into an object like x, and I say tuple of x, this of course works. But then later, if I say list x, I want the list out of it. Oh, this works too. Wonderful. I had no idea that this did work. So many of these lazy sequences, they cannot be reused. So remember that. You might have x's here that you do a tuple of x, and then later if you do a list of x, or it'll give you an error. I had no idea that it can be done for a range. But we have these very easy ways. So instead of having to write this by hand, right, I can easily write tuple range of 1 and 20. And now, actually 2 and 20, right? And now, since all I need to do is change this number, I can go and say, oh, why not make it 1,000, right? So I can go and run this again, and I'm going to get all the primes from 2 to 1,000. Okay? But remember, this helper is not what we originally wanted. We wanted a function that prints primes up to a limit. So we're going to say def primes limit. We're going to put this helper inside, and we're going to return, and we're going to say helper of tuple of range of 2 and limit. Okay, so here, instead of printing the helper, we're going to say primes limit 1,000. Okay, so as we run this code, yeah, sorry, has to be indented like this. Python is indent sensitive, so everything that is inside this function has to be indented by at least one tab. One tab is typically 4 spaces. Have I saved? Probably not. Let me save and run, and here we go. Okay, we're going to go to 10,000. It's interesting to see how fast it is. And we have blown the stack. I'm going to explain what this means at some point. All right, and don't worry about it right now. Okay, so we can compute up to 1,000. That's good enough for us. Questions? Yes. No, that's not Python. You need to be in a text editor. Like this is a text editor, right? You saved. Where did you save? Yeah, you see, you weren't in the right place, and now you say Python here. Okay, everybody has managed to run this? Yeah. Okay. Another interesting sequence is permutations. All right. So if I have a set like a sequence 3 to 4, let's say, right? The permutations of 3 to 4 would be, so 2, 4, the original one would be there, and then 2, 3, 4, and then 3, 4, 2, and then 2, 4, 3, right? 2, 4, 3, and then 4, 3, 2, 3, and 4, 3, 2. Right? These would be the permutations. Clear? So having an arbitrary sequence, we would like to produce the permutations of that sequence. Now, before we proceed, I would like to define another helper. Okay, so keep that in mind. We're going to go there. I wonder how do I comment automatically? And toggle line command, toggle block command. Okay, so commands can be expressed like this as well. So begin with 3 quotes and end with 3 quotes. So we're going to leave it there. So let's say I have a sequence of sequences. So 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. Right? I would like to have the flattened sequence, which would be okay. So let's first write a function that does that. So we're assuming that our input is something like this, and we want to produce this. Yes? So that's Option Shift A. Let's see if I can do that.
Sorry, is this space necessary?
Which space?
The space between 4 and 5.
It doesn't matter. So normally we leave a space after the comma. And when I type very fast, sometimes I forget it. So it's not. Whether you put it or not, it's just nice to have a space after the comma in general. Right? So if you're typing in Word will bug you that you don't have a space after the comma. As a matter of style. All right, so this is a very simple function. We're going to call it flatten. And we have a tuple t, which is a tuple of tuples. Right? And if, so return. So again, we're going to have something if len t is greater than 0, else the empty tuple, right? What do we put here?
Like you want to take separate entries from the tuple.
Uh-huh.
So you want to take out 3 tuples into
So T0 will be a tuple right now, right? And so I have to do something with T0, and I have to do something with T1 or onwards, right? What do I do? What do I do with this guy?
You take out anything that's already in TA.
And there has to be a recursive call as well, right? That has been the pattern so far.
Can we like determine the length of the tuple, and then that's how many recursive calls would be to take out every.
It's a lot easier than that, right? What if I just do that?
Oh. Oh, cool.
Right? So I'm going to take this input. Okay, too many brackets. Okay, so let's not print this anymore for the time being. And we execute this, and we get what we were after, right? So we're trying to flatten this list. Let me put some spaces here so that it's more obvious what we're trying to do. So this list of lists, we're trying to flatten it. And what we got was the flattened sequence, right? Yes?
I'm denied permission to access code basically.
Your computer doesn't work.
No.
No, but that data shouldn't be able to do.
Like even if I try.
So this is your code, right? Okay, cool. Where's your text editor? What text editor? Oh, it's text editor. Okay. No, that one is good. This one is good. All right. So. Okay, so this works. Go. Extra space here. All right, permutations. So we always try to solve the problem in terms of the solution to a smaller problem, right? That's kind of the pattern that we have had. So if I go back here, right, for powers, right, when I'm trying to solve the problem of size k, I'm going to make it so that the solution for size k is defined in terms of the solution of size k minus 1, right? So that's an important trick. So I start from my current problem, and I try to apply a helper, but to a smaller size, and size keeps decreasing until I get to the trivial case, which has a trivial solution, which is the empty sequence, right? So previously we tried to do the same thing, right? So for the limit, right, we have a limit, and then when we apply helper, right, this set will have fewer elements. The limit is the same, but the first element has increased. So the difference between the first element and the limit has increased, right? And we're going to keep increasing that first element until it reaches the limit. So what we have to compute is an empty, we have a trivial solution, right? Because if I want to compute all the prime numbers starting at 100 and up to 100, then what I have to produce is the empty sequence. Right? Does it make sense? Yes? So let's think about permutations. So I want the permutations of 1, 2, 3, or 2, 3, 4. Let's do the simple case. It's easier to follow if we have, well, actually, let me go here. I have 1, 2, 3, and I'm going to not give you the spaces. Now, let's say I remove either 1 or 3, one of them, right? Which one you like removed? Let's say we remove 1, right? We remove 1 from this. So we are left with the sequence 2, 3. What are the permutations of 2 and 3? 2, 3, and 3, 2, right? These are the permutations. Having this set of permutations, can I produce the permutations of 1, 2, 3 quickly? Yes, right? How is that? Well, I'm going to take this one 3 times. So the missing element is 1, right? And I'm going to insert 1 in all places where it can be inserted. So at the very beginning, in the middle, and at the very end. And then for 3, 2, I'm going to do the same. I'm going to insert it at the very beginning, in the middle, and at the very end. And I have obtained all the permutations, right? So if I somehow magically obtain the solution for the smaller tuple, I can use that to create the solution for the current tuple. Yes? So let's try to do that. So def of a tuple T. Okay. And we're going to learn a trick now. We're not going to have a helper anymore. We don't need a helper. So I can compute something and give it a name, right? Essentially. Put it into a storage place. Give it a name, right? So I'm going to say smaller equals permutations of T from 1, 2, and onwards. Actually, I'm not quite sure I need this smaller. So the permutations of the empty tuple is the empty tuple, right? There's nothing to be returned. But the permutations of a singleton, of a tuple with one element, is sorry. The permutations of the empty tuple is the sequence containing the empty tuple, right? What do you mean one? Yes. So it's one permutation, which is the sequence containing the empty sequence. And the same, if I have a tuple of one element, it's going to be not that element, but the tuple containing the tuple. Yes? Right? So this is going to be like 1, 1, comma. Right? Whenever we have a single element, we have to put a comma there to make it sure that. Maybe we don't need this. Let's not jump the gun, right? So if our tuple is empty, we're going to return the tuple containing the empty tuple, right? So we need a comma here. So if len t equals 0, else, right? So now the interesting thing is that the permutations of T1 is going to give me the solution for the smaller set, right? And then for x inside in those permutations, what do I want to do? I want to take T0 and insert T0 at every single space, right? At every single position. Okay? So I'm going to say x in permutations. So I'm going to have 4x in permutations. And then, how many positions do we have? Well, it's x. X can have any length. 1, 2, n. So if the position, if the length of this is one of the x's, right? It has a size of 2. In how many places have we managed to insert? 3 of them, right? So it's length of x plus 1, right? So for x in permutations, for I in range of 0 to len x plus len x plus 1. And what do we want here? Actually, we might not need the flatten. I'm realizing right now that we might not need a flatten. What do I want here? How do I do the insertion?
Plus.
So T from 1 to I, if I is 0, it is going to be empty, plus tuple 0 plus T I onwards, right? right? So if I is 0, it is going to be empty. So we put t0 at the very beginning. If I is len x plus 1, this one is going to be empty, right? Which means that we're inserting at the end. T0 goes right at the end. Okay, let's see how good a job did we do. So print permutations of 1, 2, 3. I'll just delete this. And for some reason, we get some extra permutations printed out. Let's try to figure out why. But we're almost there, right? We're not very far. So you can see that from here, we have correct permutations. We also have a bunch of missing ones. Why do I say t here? X. You should correct me. X, right? It's this X. Okay. Still not completely there. So so assuming that we get a permutations, how many numbers do we get? 5. Mm-hmm. Which one? This one?
So yeah, so return at the else top of the whole line. Can we go through it slowly?
So if X is in permutations of the smaller set, right? So this would be the permutations of 2 and 3. So I get 2, 3, 3, 2 from here, right? Now this X has a range, has a length of 2, right? So I will go from 0 to 3, right? So it was going to be 0, 1, 2, right? So what are we going to do? For every X and for every I, we're going to compute X from 1 to I, X from 0 to I, Y 1 to I, sorry, 0, right? So X up to I, right? So I'm going to take all the elements up to I. I want to insert T0 in the middle of X, right? How do I insert? I want to insert that position I. Well, I'm going to take all the numbers up to I. Then I'm going to put T0 in the middle. Then I'm going to take all the numbers from X, from I onwards. Remember, here I is exclusive, and here I is inclusive. So if I is, for instance, 1, this will be X0 only. I don't include the 1. And here I go from 1 onwards.
So it's just because of the nature of the language, it's exclusive.
Yeah, but this is standard in computer science, right? So the left limit is inclusive, the right limit is exclusive. Everywhere in programming, whenever you look at ranges, you're going to want, you can't have both inclusive or both exclusive, because then either you include some elements twice or you exclude some elements, right? You want one to be inclusive, one to be exclusive. And the convention is the left one is inclusive, the right one is exclusive.
The parentheses, I don't say that. So top
These parentheses,
yeah, so the first parenthesis it covers from the beginning to the end. So you want
yes, up to here. Okay, let's make it. Let's align them a little bit. Okay, is this better? right? So I have this expression. So I'm going to have this element for x in here and for I in here. Okay? And there we go, we have all the permutations. Does that make sense?
So it's tuple and then have like so it's tuples inside of a big tuple.
Yes. Okay? All right, subsets. So I'm just going to delete this because I think they're not really useful. I'm going to comment these for the time being, though I'm going to uncomment them when I release the file. All right, subsets. So say I have the tuple 1, 2, 3, 4. What would be the subsets? Empty. 1, 2. So to make it very easy, all right, I'm gonna make it like this, right? So then I'm gonna have 1. Let's just do 1, 2, 3 because I don't want to do 16 of them. So 1. I'm gonna have 2. I'm gonna have 3. And I'm going to have 1, 2. Then I'm going to have let's say 1, 3. Then I'm going to have maybe this is empty, and I'm going to have 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, right? 1, 2, 3, 4, 5, 6, 7, 8, all of them, right? So what do you see that? And if I have done a better job at putting them in the right order, they would have been better, right? So you see that each of the numbers appears 4 times, right? So 1 appears 4 times, 2 appears 4 times, 3 appears 4 times, right? And it's 2 to the power of the size of the original set, right? And let's see how to put them better. Control V here. I'm trying to put them in a better order. Okay. Right? So notice that 3 appears alternatively. 2 appears in burst, right? So we have 2 empties, 2 twos, 2 empties, 2 twos, right? And then for ones, we have 1 appearing, not appearing 4 times, and then appearing 4 times, right? So there's a pattern. We have a pattern of producing sets, right? So in producing subsets, so now we're going to have to learn about giving names to things. So def subsets, and we have our tuple, and if the tuple is empty, and we're going to deviate a little bit from, so if the tuple is empty, we're going to return what?
Like a tuple with an empty.
Yes, so the tuple containing the empty tuple. This is the tuple containing the empty tuple. Notice that we're going to use return multiple times, and we're using a different type of if. So we're learning that right now. Else, and now, and I'm going to explain, right? But essentially, we're testing from the very beginning. We're not returning one big thing. We are allowing ourselves to have multiple return statements. So if the length is 0, which means tuple is empty, we're going to return the empty tuple. Otherwise, we're going to compute the subsets, right? S equals subsets.
Well,
Yes?
where's the conditional in the if statement?
Again?
Where's the conditional in the if statement?
What do you mean the conditional?
Like, is it if length equals to 0?
If length t equals to 0, yes, that's a good point. All right, so if length t equals 0, return the empty statement, right? Empty set, and then otherwise, let S be the subsets of the smaller set. Right, we remove one element and let's get a subset. And what do you do now?
We use the optimization.
No, not quite. So let's look here. So what are these?
All the subsets of 2, 3.
Yes, very good. So those are the subsets of 2, 3. What are these? Compare these louder.
Like subsets of 2, 3, and 1.
So it's the subsets of 2, 3, where to which of them I have added 1, right? So this guy is my S. This S, right? So I have half the result here. So my result is going to be S plus something. What is that something? T0 plus X for X in S. Okay? Now it's very important, since I'm using S twice, it's very important to give it a name. I don't want to have subsets twice. This will increase the complexity. This will increase the time of computing extremely by a lot, right? So we don't want to do that. But do you understand now this? So X plus and tuple, let's put it like this. Right? So I take every X in the subsets and I add to it the first element that we have removed here, right? Yes? So let's see the subsets. I'm gonna, okay, we're stopping the permutations. So if I run, okay, S plus, let's add backslash there. Python is a bit stupid sometimes, right? So these are all the subsets. Okay? So hopefully this whets your appetite for thinking recursively and trying to apply your math into programming. Okay? So there's two ways to approach programming. One is from math, which is always what I have preferred, and the other is to look at everything as a sequence of operations, right? Which might make you more effective if you don't have a math background, but will not allow you to grow as a programmer later. So math is also always a very useful resource. So this is the lesson for tonight. I promised homeworks. Whoa, my